Hi, so we're back. So as a prelude to discussing the Navier-Stokes equation, which we've really seen in an overall guise, what we did was we did a few things with regard to streamlines and Bernoulli constant and vorticity and things like this. So I figured I would recap things a little bit before moving on. We kind of stopped at vorticity, and what we're going to do next is talk about circulation and how this is a quantity that's conserved. And then we will talk about a very interesting effect called the Magnus effect. So, but before that, I figured we would do a very quick recap of what we've done so far, especially during the last lecture or two. Yeah. So, what we first said was that if we are talking about an irrotational and incompressible and of course inviscid flow, in this case the velocity, and for now let us specialize to 2D flows. The velocity can be expressed as the gradient of a scalar velocity potential, and we can also express, especially for 2D flows, we can also express the velocity. Since it's 2D, I'll explicitly write this as xy as the curl of something called a stream function. So this is the potential, this thing, and this thing is called the stream function. So if all these conditions, irrotationality, incompressibility, inviscid, and 2D, all these conditions are satisfied, and they very frequently are, both these hold, okay, and in which case it turns out very interestingly that also, okay, in other words, both phi and psi are solutions to the Laplace equation. Okay, both of these. What's more, these are orthogonal. In other words, the potential lines and the stream lines are orthogonal, very much like electrostatics. Okay, so this is one thing we said, and what is more, as a consequence of this, it's as though ux and uy are components of a single complex variable. And this property enables us to make to apply the theory of complex variables. You don't have to solve for ux and uy separately, and this simplifies life a lot. And this comes from the Cauchy-Riemann conditions, which is essentially this. Okay, so this is something that we said, and we showed that as a result of this, as an example, we looked at the problem of a smooth sphere and velocity streamlines around the smooth sphere, which would look something like this. We've drawn these and the velocity streamlines very far away would simply be undisturbed, as though the sphere was not there. And okay, so this is for inviscid fluids, and applying the appropriate boundary conditions, which is that the normal component of velocity here on the surface of the sphere is equal to 0, and the tangential component of velocity very far away from the sphere is undisturbed. It's what it would have been in the absence of the sphere. And so we need two boundary conditions in order to solve for either this or this. Right, so there's a second order differential equations. You need two boundary conditions, and these are the two boundary conditions. And it turns out that the solution is something like this. Some like so, plus u a square over r square, where a is the radius of the sphere, plus, right. So this is written in polar coordinates, and there's a little bit of mixing here between coordinates, but you understand what we're talking about. This is really, x is really r cosine theta, and so this solution, which is essentially, which we can simply write down, knowing the solution to this in polar coordinates, which is well known, and applying the two boundary conditions that we talked about, you can immediately write down the solution. Want to emphasize, so this is an example of how these are very useful. You can immediately write down the solutions to these from very well known solutions, and I want to emphasize that this is really only an exterior solution, not the interior one. The interior solution, interior to the sphere, in any case we're not interested in, so we're only interested in the exterior solution, but just want to emphasize that, right. So the other very important point we discussed was the Bernoulli constant. Right. So the Bernoulli constant is essentially, how should I say this? It's essentially an energy equation. Okay. So we start with the Euler equation, which, if you remember, is a momentum equation. In other words, is F equals ma in the absence of viscosity. Okay. So you write down an ma on the left hand side, and the F on the right hand side has to be due to pressure gradients, in other words a gradient of P, or due to body forces. These are only two things possible. So writing it down exactly in that spirit, the Euler equation is, which is the momentum equation for inviscid fluids, and you should ask yourself, the moment you see a partial u partial t, you should know that we are writing this down in the lab frame, in the Eulerian frame. So this would be ma, and the F would be gradient of a scalar pressure plus any possible body forces, which we will assume that this can be written as minus phi. Or mind you, this phi is different from the phi we talked about earlier. This is the gravitational potential, not the velocity potential. Okay. So if we can write this down and do a little bit of trickery with this, and you integrate over a streamline. So this is what we do. So mind you, this is this is F or that's F. Either way, the way it's written here, this is ma and that's F. But what you're really doing is right. This is what you're doing, and what do you get when you integrate force over distance? You get work, energy, one of these things, right? So that's exactly what you get. You get a quantity that's energy per gram, okay? And it turns out that the result of this integration is this quantity. I write this down again just to emphasize how important it is. And I want to write this along a streamline. Okay, we get this quantity, we get this particular property, which is half u squared plus, let me write this down technically correctly, but I just want to emphasize that many times people just write this as p over rho. We get this very important result, yeah, which is the Bernoulli constant. The Bernoulli constant. So this is essentially the Bernoulli constant right here. Just to remind you, the phi is not the velocity potential, it's the gravitational potential. So let's go back to this slide here, right here. See, it's this. Okay, so this, you get this by integrating, you arrive at this result by integrating the f along a streamline, and you get the Bernoulli constant. And there are many interesting, so so the other thing is, this is constant along a streamline. It is one constant along one streamline, it's another constant along another streamline. So I want to emphasize that. And this enabled us to look at some nifty things, such as the following, the water out of an orifice like so. Right? You followed a streamline, you followed one streamline all the way like this, right? And made use of the fact that 1/2 u squared plus p over rho plus phi equals constant, right? You made use of the fact of this fact, and the fact that p does not vary much between here and here, yeah, and said that phi is essentially g times h, where h is the height, and this enabled us to figure out the well-known result that the velocity of the fluid flowing out is square root of 2gh. This is one thing. The other thing we did was, and I'll say this very briefly, we considered an airfoil that looks somewhat like this. It's essentially a section of an airplane wing, and by considering one streamline that goes all the way across the airfoil, yeah, and knowing that the Bernoulli constant is constant all along the streamline, and the fact that the airfoil is designed such, again, since the airfoil is very, very thin, phi is pretty much the same above and below, yeah. But unlike this situation, the airfoil is designed in such a way, in other words, the airfoil is cupped like so, such that the velocity here is lower than the velocity up here. As a result, in order for this quantity to be conserved, the pressure here, the pressure at the bottom, P bottom and P above, the P bottom is greater than the P above. As a result of which, you get a net upward force. This is a very, very simplistic, very elementary explanation for why there would be a lift on an air wing, on an airplane wing, a properly designed airplane wing, one which ensures that the velocity at the bottom of the wing, the velocity of air at the bottom of the wing, is lower than that on the top of the wing. If that's the case, then going by the Bernoulli constant, the pressure at the bottom will be larger than the pressure above, and therefore the wing experiences an upward lift, right? So this is the other thing we discussed. And finally, we came to the concept of vorticity, okay, which we know is a curl of u. It measures the rotationality. And as we've discussed several times before, really it's only in a viscous flow that you expect the flow to be rotational. Okay, and this brings us to, just this is enough to sort of anticipate one of the results that's coming up very soon, which is that there's an analogous, there's a closely related quantity called circulation, and this quantity is conserved in an inviscid flow. If there's no viscosity in the flow, if for whatever reason there's a rotation, if for whatever reason there's a circulation in the flow, it's conserved. It does not change. There's no scope for generation or suppression of vorticity in an inviscid flow. Okay, so what we sort of did was, again, we started with the Euler equation. Again, written down in the lab frame. And now we're simply writing this down. This is essentially your G as the previous example, and we took a curl of the entire equation. Okay, and then you take curl on both sides. That's what we do. Okay, so take curl of everything and assume that the fluid is barotropic. In other words, the pressure, straightforward function of the density. In this case, it turns out that this one and this one are parallel, and that leads to a very important simplification, and that will lead us to equation to a dynamical equation for the vorticity. Which is, I really should be putting a vector sign on top of this, is equal to so this is an equation, although there's a u here which is sort of the uncurl of omega, but still this is really a dynamical equation for vorticity in that it relates the time derivative of the vorticity with space derivatives of the vorticity. So you start out with a certain distribution of vorticity in the flow for whatever reason, and this equation gives you, with proper boundary conditions, of course, this equation completely tells you how the vorticity is going to behave as time progresses. Right, and what's more, you specify the and since this is all of this is for incompressible fluids, in other words, okay, so that already specifies the divergence of the flow, and this specifies the curl of the flow because omega is the curl of u. Specifying both the divergence and the curl of a vector field completely specifies it for certain, for well-behaved fields which die off nicely at infinity, and or if you're not willing to consider boundary conditions at infinity, you have to specify both these equations on the boundary subject to those caveats. It's a well-known fact that specifying the curl and divergence of a well-behaved vector field specifies it completely. So it's in that sense that we say that the entire velocity dynamics is completely specified by this equation, by the dynamical equation for vorticity. And from here on, we will discuss what's called the Kelvin vorticity theorem, which essentially says that there's this quantity that we'll specify, which is called K, which is the circulation. And this theorem essentially says that in an incompressible inviscid flow, the circulation K is conserved. If for whatever reason there's a circulation in the flow, it remains as it is. if there's no circulation in the flow, you cannot generate circulation. Okay, so this is essentially what Kelvin's vorticity theorem tells you, and we will consider that when we meet next. Okay, so that's it for now, and thank you.